Hi, I'm Professor Chris Rose, the Arcane Logician. Any logician should understand Gödel's incompleteness theorems, and anyone who has used ChatGPT or entered in a Google search recently understands the impact of artificial intelligence. Now, this phrase, artificial intelligence, might not be quite right. Perhaps machine learning or large language model is better. Whatever you call it, the impact of this thing is definitely there. It turns out Gödel's first incompleteness theorem has implications for artificial intelligence. Specifically, I'm talking about the outer limits of AI. Yes, the discussion does get pretty philosophical, but it does touch on the distinction between humans and machines. I think it's fascinating. Let's get started. We begin with some background information, starting with formalism. Formalism is a position in the philosophy of mathematics, famously held by Hilbert. Hilbert was a very well-known mathematician. There's a summary of formalism given here. It says, math arithmetic is a formal game of symbol manipulation that humans play. So the formalist would say math is just a game that humans made up, like tic-tac-toe or chess, that we simply play. So that's what the formalist would say. Then along came Gödel's incompleteness theorems. We are interested in the first incompleteness theorem, which is given here. It says, for any consistent, recursively axiomatizable formal system capable of encoding arithmetic, there is a true statement the formal system cannot prove. So the moral of Gödel's first incompleteness theorem is truth transcends provability. That's one way to think about it. Well, it turns out Gödel's first incompleteness theorem dismantles Hilbert's formalism. And the idea is that for any formal system you present that you claim encaptures all of mathematics, by Gödel's first incompleteness theorem, there is a statement, a true statement of mathematics the formal system cannot prove. And so the formal system does not capture all of mathematics. So mathematics goes beyond any specific system you present. Gödel, in fact, saw his first incompleteness theorem as an argument for mathematical Platonism. Mathematical Platonism is a position in the philosophy of mathematics which says math has pre-existent transcendence. So unlike the formalist who thinks math is just a game, according to mathematical Platonism, math is more than a game. There's something more there. Here it says mathematical Platonism says math is discovered, not invented. So that is another important aspect of mathematical Platonism. Well, I tend to agree with Gödel. His first incompleteness theorem, in my view, does sufficiently dismantle Hilbert's formalism, and his first incompleteness theorem is a great argument for mathematical Platonism. So having established that, it turns out Gödel's first incompleteness theorem has profound implications for AI. In a moment, we will continue the discussion on the connection between Gödel and AI. Welcome back. We continue our discussion on the connection between Gödel and AI. To do that, we will introduce a version of Gödel's first incompleteness theorem called weak Gödel's theorem. Weak Gödel's theorem does a really good job at explaining the key difference between humans and machines, or humans and computers. Although to really understand weak Gödel's theorem, we must first understand the halting problem. The halting problem is a famous result from computability theory due to church Turing around the time 1936, 1937, the halting problem could be stated as follows. There is no program that can distinguish between good programs and bad programs. And so your question might be, what's a good program? What's a bad program? A bad program is like when you type in some code, hit enter, and the program runs on an infinite loop, or the program does not come to a conclusion. A good program is a program that tells you an answer, a program that comes to a conclusion. And it turns out there is no program that can beforehand distinguish between the good programs, the ones that come to conclusions, and the bad programs, the ones that don't come to conclusions. The proof is straightforward. If P was a program that could distinguish between good programs and bad programs, then simply copy and paste the code of program P into the code of a new program, program D, and define D so that it defies whatever P says. So, for example, if P says, hey, this program comes to a conclusion, then D will run forever. If P says, hey, this program runs forever, then D will come to a conclusion. Interestingly enough, if you take the code of program D and insert it into program D itself and ask, hey, does this thing come to a conclusion, or does it run forever? You actually get a contradiction. And that's how the halting problem goes, which leads us to Gödel's theorem. Gödel's theorem could be stated as follows. For any program P, there is a true mathematical statement S, such that P cannot determine if S is true or false. Unlike Gödel's first incompleteness theorem, we're no longer talking about consistent systems of mathematics. And now we're talking about using computers and programs to determine the truth of mathematical statements. So it's a little weaker. It's a subcase. The proof goes as follows. We can turn good programs into true mathematical statements and bad programs into false mathematical statements. And if there was a program that could distinguish true math from false math, this program would also distinguish between good programs and bad programs. And that contradicts the halting problem, which we just discussed. The key takeaway is this applies to any program/computer P, that they always have a statement S such that they cannot determine whether S is true or false. However, look at the theorem statement. There is a true mathematical statement S. So us humans, using rigorous deduction and logic, can determine that S is true. However, give P unbounded time, unbounded memory, all the rigorous deductions and logic it can handle. P would never be able to determine whether S is true or false. So this is a fundamental distinction between us. The implication is that a given human is distinct from a given computer/program, because for any computer/program, they always have this sentence S such that we can determine that S is true, but they can't. And this applies to even the most powerful programs. Imagine a very powerful large language model. They still have this sentence S such that they cannot determine whether S is true or false, but we can rigorously show that S is true. So perhaps this means that we have access to some sort of Platonic realm, and that humans and computers are distinct in that way. There's a lot of things this could mean. One thing it means, one implication, is if you're a philosopher of mathematics, that you will always be employed, or at least have a fair shot at employment, because this means that computers and programs are very bad at philosophy of math. The reason is because in order to do philosophy of math, you need to be able to determine that S is true, because you need to be able to reason about Gödel's first incompleteness theorem and things like that. You need to be able to handle things like that. And we have learned today that a computer/program will never be able to really determine things about S. And so a computer/program will be pretty bad at philosophy of math, or will not be able to really pioneer philosophy of math in any sort of meaningful way, or at least there will be a way in which humans will be able to pioneer the subject that is different from the way computers will be able to be applied to the subject. So what do you think? The whole area is very interesting, and just wanted to lay some thoughts down. If you like what you are hearing, please click subscribe. Give some recommendations in the comments for future videos. Have a nice one.